Okay, we're continuing to talk about functions and their inverses. And so here is, let's see, this is just about functions and their inverses. Here is, I want to discuss, like, some functions have inverses, some don't. So real quick, if we think of, let me just draw some basic graphs. Some basic functions. These are some ones. Here's one, and here's one. And here's one, and here's one. These are sketches, and let's see, here's one, and here's one. These are known as the basic graphs. And so these are not very well drawn, but that's okay. We're going to kind of try to figure out which ones I drew on here. This one is y equals to x squared, and this one is y equals to the absolute value of x. And this one is y is x cubed, and this one is y is the cube root of x, and this one is y is the square root of x, and this one is the reciprocal function, y is 1 over x. And so those are poorly drawn, but those are just sketches of the basic functions. But they're all functions because they all pass what's called the vertical line test. If I were to pass a vertical line through each of these functions, it would only touch in one place. And so that makes it passes the vertical line test. So we say, okay, yes, it's a function. Now there is something called the horizontal line test, where if you pass a horizontal line through this and it only touches one place, then it passes the horizontal line test. What does that mean? Well, if a function passes the horizontal line test, it is called one-to-one. And that means for every individual input, it has its own individual output, and it doesn't have, they don't share outputs of any kind. Why is that important? Any function that is one-to-one means you can find an inverse function for that. It has an inverse, exists for that. So some of these have inverses, some of these do not. So let's have a look. Let's just pass the vertical line through a horizontal line through this, and I would say this one is not one-to-one. This fails the horizontal line test, meaning there's no inverse. This is the absolute value function. No, not 1, 2, 1. So over here I wrote it fails the horizontal line test, and over here I wrote not 1-to-1. Those basically mean the same thing. Right here, oh, yes, it has an inverse. Okay, so what could I have written here is it passes the horizontal line test. It is 1-to-1. It has an inverse. That is, I'm basically saying the same thing. That means all of those things. So right here, does this one have an inverse? Well, does it pass the horizontal line test? Is it 1-to-1? Those are all asking the same question, and the answer is yes. It's 1-to-1. So it does have an inverse. How about this guy? Yes. How about this guy? Yes. These all pass the horizontal line test. They all have an inverse. They are all 1-to-1. These two do not. But there's something, some of you guys are taking trig, so this is just an interesting thing to look at. If you think of, let's just say the sine wave. You could do this with cosine as well, or tangent, or cotangent, or secant, or cosecant. Let's just pick sine. The sine wave looks like this, basically, right? And it goes on forever, right? Does this fail, or does this pass the horizontal line test? Well, it fails. It fails pretty miserably, right? He totally fails this in lots of places, right? He's all over the place. He's failing it. But that does not stop trig books from writing something like this. They might say, oh, go ahead and find sine inverse of something. It does have an inverse. Now, how in the world can sine have an inverse if it totally fails the horizontal line test? And this is how. They restrict the domain for sine. So let's just say this right here is pi, and this is 2 pi, and this is negative pi. They say, let us only look at certain values of x. Let's restrict his domain from here, negative pi over 2, to here, pi over 2. And we're only going to look at this part of the sine wave. Okay. And so we don't look at any other part of the sine wave because it's periodic and it repeats itself. And so what they do is say, let's restrict the domain. When we talk about the sine inverse of x, we are only going to look at values between negative pi over 2 and pi over 2. And if you look at this stretch, this part of the graph, it passes the horizontal line test. So for this much of the sine wave, you can find an inverse function. They might do that in math for other functions. Look at this, y equals 2x squared, for instance. What if we say, okay, I want to only look at this for x values that are greater than or equal to 0. In that case, you would not look at any of the negative values, and in that case, it would pass the horizontal line test, and it is one-to-one. So sometimes we do that with functions. So that's just something I wanted to point out to you. So on your worksheet there, let's see, we have some things to answer, and we can answer a lot of these blanks pretty quickly because of the last video we talked about. So if you look at the last video, it's going to help you answer 27 through 36. For a function to have an inverse, it must be, and what you would put right there is 1-to-1. That's what we were just talking about. So let's see. 31, if the point AB lies on the graph F and F has an inverse, then what point must lie in it? That has to do with domain and range being switched. BA. So lots of that was covered in the last video. You can answer 27 through 36 basically by what I talked about. Let's move on to number 38. It says, use the definition of inverses to show analytically that f and g are inverses. Another way I might put this is determine, you might have to do this. Here's another way I could word that. I would say determine if f and g are inverses by using compositions. And so what this is telling you to do is take this composition and this composition of functions, f of g of x, g of f of x, and see if they both equal to x. If they do, then you can say, yes, they're inverses. If they don't, if you get something like x plus 1 or the square root of x or x squared, that's not regular old x. That is not an inverse. You would say no. So let's see. For number 38, let's do that one. For 38, they give us that f of x, where f of x is equal to 4x plus 3. And then they tell us that g of x is equal to x minus 3 over 4. So I'll do it for this one. Okay, so let's take f of g of x. Well, this is equal to f of, and what you should do is replace the innermost with what it's defined to be. So what g of x is x minus 3 over 4. So I put that in there, x minus 3 over 4. That replaced my x. Okay. So now I go to the f function. I'm only looking at the f function, and wherever there's an x, right here, it's getting replaced with something. What are we replacing that with? Well, whatever we find in those parentheses. So what we found in the parentheses was x minus 3 over 4. X minus 3 over 4. Now I'm just going to simplify that. This is really 4 over 1 times x minus 3 over 4. The 4 will go into 4 one time. 1 times x minus 3 over 1 is x minus 3 plus 3, which gives me a regular old x. Okay, let's do it the other way. What is g of f of x? Okay, this is g of, replace that f of x with what it's defined to be. Well, f of x is defined to be 4x plus 3. 4x plus 3. 4x plus 3. Okay, so then we'll say, go to the g function, and here's the g function. So what's going to happen here is this x right here, which is in the numerator, is getting replaced, and it's getting replaced with whatever I find right there. So what I find right there is 4x plus 3. Now, I don't actually need those parentheses. I wanted them to help me group something together, but when there's a positive 1 in front of it, you don't actually need it. So I'm going to erase that and say, now I can combine. 3 minus 3 gives me 0. So this is just 4x divided by 4. 4 goes into 4 once and I get x. So I found that if I take f of g of x, it simplifies to x, or if I take g of f of x, it simplifies to x. And so when that happens, you can say, yes, these are inverses. All right, cool. So that would be number 38. If we go down to 43 and 44, 43 I'll do real quick. I'll just say it out loud. This will be fast. Determine whether each function is 1 to 1. If so, find its inverse. When I look at 43, it's a set of 5 points. The fact that there are no repeated x or y values means it is 1 to 1. And so it does have an inverse. So the inverse, this is based on the fact that the domain and range are switched. So for 43, you would say the inverse for that would be the set of points 4, 10, 5, 20, 6, 30, 7, 40. So all I did was reverse the x and y. So I think you guys will be able to do 44, no problem. 49 through 54, I'll just talk this out. 49 says, here's an everyday activity. An inverse undoes what the operation does. So for instance, if I have to find an inverse operation to 49, which is tying your shoelaces, what would totally undo that operation would be, the inverse would be untying your shoelaces, just like that. So I think you guys can go through this. There is one that's a little bit tricky, and that's number 50. And number 50 says pressing a car's accelerator. And so what everybody wants to say that the inverse operation to be, for this to be, would be pressing the brakes. But that's not an inverse operation. And the reason we all say that is because we're good at driving. But the inverse operation to pressing a car's accelerator would be releasing the car's accelerator. That would totally undo the operation. If you think about it, pressing the brakes is a totally new operation that you've introduced. That would not be F inverse. That would be some other new function called G. So just that's a little bit of a tricky one. The rest of them I think you can do. Let's jump on down to 73 and 76, and this is the operation of how to find an inverse function. So it's a real quick 4-step operation. How to find an inverse. How to find f inverse of x. Number 1, replace f of x with y. Number 2, interchange x and y. Number 3, solve for y. Number 4, replace y with f inverse of x. So it's a little 4-step operation. I'm going to find the inverse of the function that I introduced in the last video. I'm not sure if I remember it, and I don't have it written down, but let me just go through the motions of how I would do this. What if I think I gave us some, I said f of x was equal to x plus 1 cubed minus 2. Maybe it was something like that. If it wasn't exactly that, it doesn't matter. It's the same operation. I'm just going to do this 4-step process. Number 1, replace f of x with y. Okay, y is equal to x plus 1 cubed minus 2. Number 2, interchange x and y. Okay, so let me interchange x and y. And while I'm doing this, I'll make it purple. So x is equal to y plus 1 cubed minus 2. Number 3, solve for y. All right, well, y is in here. It's tied up in this cubic thing. So I need to isolate this first. So I'll add 2 to both sides. And then to free it from this cubic thing, I'm going to take the cube root of both sides. So the cube root of this is equal to the cube root of that, and the cube root of something cubed undoes each other. I just have x, y plus 1. Now I'm going to subtract 1 from both sides. And then step number 4 says to replace y with f inverse of x. So this is how I found the inverse function a minute ago when I was doing that on the other video. So there's a couple of problems on here for you guys to try that for. I'm going to do 76 with you because that can get a little tricky. Let me do 76, which says f of x. F of x is equal to x over 1 minus 3x. Let's go through this one to see how we would do that. Okay, number 1, replace f of x with y. So I'm going to say y is equal to x over 1 minus 3x. Y is x over 1 minus 3x. Interchange x and y. Okay, x is equal to, y over 1 minus 3y. Okay, and now it gets a little tricky. Solve for y. That's why I wanted to do this one with you. First thing I'm going to do is kill my fraction by multiplying both sides by the denominator. So when I do that, times 1 minus 3y, 1 minus 3y on both sides. These will cancel, and I'll get y is equal to, I'm going to distribute the x. X minus 3xy. X times 1 is x. X times 3y is 3xy. So I'm trying to solve for y. So when I have this situation, the best thing to do is get all the y's on one side. So I'm going to add this guy over here. X is equal to y plus 3xy. Now, when I would like to have one term with y in it, but I have 2 terms. But when I have this situation, a really nice thing to do is factor out the y. Then it's by itself. So I get x is equal to y times 1 plus 3x. And then I can just divide both sides by 1 plus 3x is equal to y. And then replace y with f inverse of x is x over 1 plus 3x. This is the inverse. So that had a little bit of trickiness to it. I wanted to do that with you. Lastly, on the worksheet, they have a graph. And so the graph, they ask you, it says, the graph of a function f is shown. Use the graph to find each value. So like number 85, it says find f inverse of 4. Well, f inverse of 4. So f inverse of 4. How you want to think about this is you want, since it's an inverse, not an input, you don't want to go to the x value of 4. You want to go to the y value because you're using the fact that the domain and range are switched. So go to the y value on your graph of where y is equal to 4. So I'm going to go up high to where y equals to 4. And then I'm going to go down and read the x value. And it turns out that the x value that makes that happen is also 4. So let me do one that's harder. Let's do 87. That was 85. Okay. 87 goes like this. It says find f inverse of 0. All right. So what I'm going to do is not go to where the x value is 0, but where the y value is 0. Where is my graph crossing 0? And so I see where it's crossing 0 is at the x-axis. And so where's it crossing the x-axis? At x is 2. So the output of this is going to be 2. So you have to think a little bit backwards to get through that part of the worksheet. I know I didn't do every problem, but I don't want the videos to be too long. And I think you guys can figure this out. So that's why I left some of them blank. All right, that's inverses.